Hey everyone, and welcome back. So, if you're joining us fresh off your Solana CLI token build, congratulations, you actually survived the command line. Today, we're pivoting over to the EVM. This explainer, proudly brought to you by Forge College, is going to fundamentally transform how you test transactions. We're moving far, far away from that anxiety-inducing, sweat-inducing guessing game of just hitting send and praying to the blockchain gods. Instead, we're shifting into building a rigorous, testable engineering blueprint. Let's dive right in. Okay, here's the game plan for today. First, we'll cover the pipeline model, then building the blueprint. Third, we'll walk through a concrete ERC20 example. And finally, handling divergence, because let's be real, things never go perfectly on a testnet.
All right, kicking things off with Section 1, the pipeline model, focusing on sensors and artifacts.
To start off, we really have to stop treating the blockchain like some magic black box where transactions go in and receipts just magically pop out. Instead, I want you to picture a literal industrial production pipeline. A transaction traverses 5 exact steps: creation, propagation across the network, inclusion into a block, confirmation as those blocks stack up, and ultimately, finality. The absolute secret to your capstone project? Well, at every single one of these stages, we're attaching diagnostic sensors to collect hard data. We aren't just casually observing anymore. We are meticulously measuring. You know, this right here is the exact difference between an amateur and a pro. Amateur testing is hitting send, staring blankly at a block explorer, and waiting until you feel this warm, fuzzy sense of safety in your gut. Professional simulation, on the other hand, means we instrument sensors to capture concrete artifacts, and we demand explicit numerical thresholds. We're completely leaving that fingers crossed methodology in the past and adopting the rigorous discipline of explicitly logging every single event. Moving right along to Section 2, building the blueprint. Think of this as your master checklist. This is exactly how theory turns into a highly actionable plan. This blueprint maps out the specific signal you absolutely must verify, along with the minimum physical artifact you must capture. At the creation stage, your signal is local validation, which you prove by grabbing the raw transaction hex. At propagation, you're looking for mempool visibility, proven by timestamps from peer nodes. Inclusion needs the receipt and block hash, proven by saving the actual receipt JSON. Confirmation requires you to watch the depth counter and save block headers. And finally, finality demands zero evidence of a reorganization, proven with a signed report. You literally need all of these to pass. Now, you might be wondering, how do we actually pull this off? You achieve this massive data collection through a process called instrumentation. Instrumentation simply means wiring up nodes and monitoring tools to essentially read the blockchain's exhaust fumes at every single stage. You're querying RPC endpoints, you're setting up latency logs, and you're continuously polling for block headers. Basically, you're building a machine that watches the machine. All right, Section 3, the ERC20 example. To make this extremely concrete, let's apply our blueprint to a classic capstone scenario, an ERC20 token transfer using a middleman contract. Your scope here must be fiercely specific. You aren't just saying, hey, I'll send a token. No way. You must declare exactly what you're doing, executing an approve to a middleman, followed by a transfer from to the destination. You're going to verify event logs and receipts, mathematically plot the mempool propagation latency, and assess finality against empirical baselines. And speaking of baselines, let's talk about a very specific number here, 10 to the negative 6. Instead of vague guesses about when a transaction is done, your success criteria absolutely must rely on empirical data. You are targeting a 10 to the negative 6 estimated reorganization probability. This is exactly what we mean when we say explicit numerical thresholds. You calculate the risk, and then you build your test to prove you've actually mitigated it. Using your previous measurements, you're going to define strict success thresholds, and these will trigger an automatic pass or fail verdict for your simulation. For example, you might dictate that a receipt must be observed within 15 seconds. The mempool median propagation has to be under 3 seconds across 2 independent observers. Inclusion needs to happen within exactly 3 blocks, and 6 confirmations must be reached within your monitoring window. If your simulation hits these numbers, it passes. If it doesn't, well, it fails. There's no ambiguity here. Which brings us to our final section, handling divergence. Because like any good mad scientist, we absolutely have to plan for explosions in the laboratory. We're dealing with decentralized networks, so chaos is basically guaranteed. So what exactly happens when the sensors fail or the network reorganizes right in the middle of your perfectly planned simulation? Well, if a transaction vanishes from the mempool, you do not just shrug, restart your script, and hope for the best. Instead, you consult your runbook. Your runbook needs explicit failure modes. If mempool visibility is absent, your process must dictate that you capture the full node logs and initiate a controlled retry. If a reorg is observed, you archive the pre- and post-reorg block headers to document exactly what the network did. But most importantly, never, ever attempt to claim success on a compromised run. Your failure modes have to dictate that you collect the traces, document the network anomaly completely honestly, and abort the run so your analysis remains utterly defensible to anyone reviewing your work. The core philosophy of our engineering approach really boils down to this simple mantra. Treat every checkpoint as an artifact you can attach to your deliverable. Subjective claims, they're entirely useless. Only verifiable artifacts matter to reviewers. So when you claim a transaction reached finality, you better be prepared to point directly to the receipt JSON and the block headers. Okay, before we wrap up, let's go over your homework. You need to gather these exact documents: your scenario statement, your success criteria table, your instrumentation list, your runbook, and your cleanup checklist. These documents form the concrete inputs for our next stage, because in the upcoming lesson, we're going to feed these exact documents directly into our testnet environment configuration. Having these totally dialed in is going to keep your execution focused, reproducible, and above all, safe. So, I'll leave you with this. If a transaction finalizes on-chain, but you didn't capture the artifact to prove it, did your simulation really succeed? Keep that provocative thought in mind as you prep your capstone. In the world of professional Web3 engineering, if you can't prove it with an artifact, it simply didn't happen. Thank you so much for joining this explainer. If you want to master more Web3 engineering concepts and truly level up your development skills, be sure to visit forge.college for more incredibly detailed resources from Forge College. See you in the next one.